Let us continue with the analysis of for drawing the Shear diagrams for beams up or for frames. And the process is just the same as in beams, only that there are vertical columns that we have to analyze and draw the shear and bending moment diagram in each of the members. We'll have to take note always that in our beams we have already started the drawing of the shear and moment diagrams, or specifically the moment diagrams. Positive moment is at the compression side, so we'll carry that one into our frames. This is our convention as far as the location of the moment diagram, moment values, both in the columns as well as in the beam. Some authors or some designers will draw their moment diagram of the tension side, especially for design of complex structures, because the main reinforcement or the steel reinforcement in concrete beams or columns are placed at the tension side, because concrete is weak in tension but strong in compression. So our reinforcement should be placed at the tension side. So in the drawing of the moment diagram, which is positive at the tension side, it simply would give the designer where the location of the tension bars should be placed. But in the book by Hibler and most of the books in structural analysis, will place our positive moment at the compression side. This is the common location that we are using, and to be consistent with most of the books and in the book by Hibler. Okay, so this is the one that I'm saying that always draw the moment diagram positive on the compression side. And to start, we'll just use an example problem that is for a frame having supports. The support at A and B are bent so as at point C, and B is fixed, this joint. So this joint will have three unknown values in vertical and horizontal reactions and a moment, while A and D will have, as well as C, will have only two reactions, vertical and horizontal, without moment because they are plane connected. So the process of solving this is to utilize the free body diagram of CD to solve for the reaction at C and at D with their horizontal reactions, and then transfer to the free body diagram of A, B, C in order to can solve also the reactions at A and to complete the reaction at C. Okay, so looking at the joints, we could not separate the in the competition for the reactions. We could not separate the frame at B because this is fixed. So we can only use the pin connection to draw free body diagrams of members, so we can have a simplified competition for the reactions, and we can apply the equations of equilibrium in the free body diagrams. So the solution will start with member CD. They have their CD that will carry CY vertical reaction at the C, and CX for the horizontal reaction. At D we have DY and DX. So We can use solution moment at c equal to 0 to solve for dx, which dx times 6 meters, its moment arm from point C, minus the moment of the load 15 meters per meter times 6 meters, the whole span, and moment arm is 6 over 2, which is the centroid of the uniform loading, in which we can have dx equals 5 newtons and directed to the right. Then moment summation at point B equal to 0, so that we can determine Cx. That is, since we have counterclockwise positive, this is positive and this is negative. So solving for Cx, we have 45 newtons also towards the right. And obviously, as we look at the free body diagram, then this has to be the correct values of the resultant reactions at both points. We go next to member AB and BC. We have the computed value of Cx 45 newtons. We have Cy, this is yet to be determined. And then Ax and Ay. We can start at joint A and solve for Cy. Moment summation at joint A. We have Cy times its moment arm, 1.5 plus 1.5 still plus 2 is 5 meters. Then plus the Cx, moment of Cx times 4 meters, which is moment arm of Cx from point A, and minus 50 minus per meter times 1.5 meters. Uh, this is kilonewtons only. 50 kilonewtons times 1.5 meters minus 40 times 3.5 meters. So Cy is 7 kilonewtons and directed upward. Moment summation at summation forces along x. There are only two forces, Ax and Cx. So Tx positive to the right, Ax minus Cx plus 0, therefore Ax is equal to 55 kilonewtons directed to the right. Then moment summation at joint C equal to 0. Ax already known, so our only unknown is Ey. So Ax times 4 meters minus Ay, because Ay will have a clockwise moment. This is counterclockwise positive. Then plus 50 kilonewtons, which is kilonewtons times 3.5 meters plus 40 kilonewtons times 1.5 meters plus 0. Ey is 83 kilonewtons and directed upward. Then we can now start drawing the shear moment diagrams for each member. This time we can now separate member AB from the whole frame, because we are now concerned with individual shear and moment diagrams for each member. Dx is 45, dy is 83, and the computed values. Then dx, dy still to be computed. And then we have moment in B, because we have a load here, reaction at A along the horizontal. This has to be resisted by moment, because this is capable of developing a moment from any forces that will develop moment at point B. So we use solution forces along x equals 0. There are only two forces, and the unknown is bx, and we have ax is towards the right, positive, and minus bx equals 0. Therefore bx is equal to ax equals 45 kilonewtons, but bx is to be directed to the left. Then solution force along y equals 0. We have also by and ay. So by will just be equal to ay equals 83 kilonewtons, but it's directed downward. And then the moment summation at joint B equal to 0. In B is clockwise, and this is counterclockwise, so this is ax times its moment arm minus in B. AX times 4 meters minus NB equals 0, or NB is equal to 45 times 4, 180 Newton meters, and directed clockwise. So from the computed reactions, we have now the values of the shear from point A to point B. We can also plot the moment diagram for moment. Starting with the shear diagram, we have the reference line 0, 0. This time for a column, forces or shear that will be developed to the right of the reference line is negative. Shear to the left is positive. So also with moment, the moment to the right is negative, moment to the left is positive. So that's the sign convention, and we start with 0, okay, this point, and then we go to the right by this amount. And since there is no load in between A and B, the shear here is constant. And from here, this is negative 45 kilonewtons. So we get negative 45, and then we have dx, which is 45 towards the left. It goes back to 0, so it loses the shear diagram. Okay, so starts with 0 and then closes with 0. The moment diagram, we have from this point, there is no moment here because moment is 0. So moment at B should be the area of the shear diagram between A and B. So 45 kilonewtons times 4 meters, it will be added to the moment here. But this is negative, so 0 plus negative 45 times 4, and we have a moment here, which is 180, negative 180 kilonewton meters. And from this point, it goes to point A, or it goes back to 0 because we have a moment in this positive moment, clockwise moment. So it's just added to 180, negative 180 plus 180 in B, it goes back to 0. So it also closes the moment diagram. So this describes the shear and moment diagram for member AB. We'll go next to member BC. And in member BC, we have already computed for BX, BY, and the moment. And at C, we have the CX value, CY, as well as, no, we have to compute for MC. Although we know, sorry, for the connection of point C, which is a hinge or a pen connection, MC should be 0. But we have to check that, from the computed values and applied forces for us to verify whether the beam is in equilibrium or not. So checking for the force summation at for along x, bx minus x equals 0. So it's actually 0 because they have equal values. This just verifies, or it just shows that there is equilibrium along the horizontal direction of member BC. Summation forces along y, they have by plus cy minus 50 minus 40. Is it equal to 0? We will have a question mark because we still have to compute for the values, and substituting the computed values, 83 plus 7 minus 50 minus 40 equals 0. This is 90, and this is also 90, so 0 equals 0. There is also equilibrium along the vertical direction. Then summation moment at C, at point C, equals 0. The only unknown is MC. We will solve for that MC based from the applied loadings and the computed reactions and moment at point B. So MB, this is positive because it gives us counterclockwise moment. And then minus MC, MC is assumed to be directed clockwise. Then plus 50 kilonewtons times 3.5 the moment arm, plus 40 times 1.5. and it gives us MC equals 0. Therefore, we say that the beam BC is in equilibrium. It is not moving. It is stabilized by the forces with the corresponding reactions and moment. So we could now start the drawing of the shear and moment diagrams. Starting with shear, we have the reference line 0, 0, and from point B, from 0 here, it goes up by the amount of dy, which is 83, and there is no load between the point B and the first concentrated load. So the shear is constant, 83 kilonewtons. And then from this point, we subtract the applied load of 50. So 83 minus 50 gives us 33 kilonewtons. And then 33 minus 40 downward, then we have negative 7 kilonewtons, and we have the reaction Cy 7, so it goes up to 0. So the shear diagram closes, and we have here the shading diagram, shading for shear diagram. For the moment diagram, we start with movement which is 180 kilonewtons. So this is negative. Counterclockwise movements are negative. So we have 180 newton meters. Shear here is negative 180 plus the shear area. So minus 180 plus 83 times 1.5 gives us 55, negative 55.5 kilonewton meters. Then this moment plus 33 times 2 will have positive 10.5 kilonewton meters. And then subtract this area from this amount, minus 7 times 1.5, subtract that from 10.5, and the value is 0. It goes back to 0 at point C. So we have the vertical shading, indicating that it's the moment diagram for vertical shades. For shearing, shear values, we have diagonal shading. So this represents the shear and moment of the beam DC. We have uh, maximum shear here is 83, maximum moment is 180. Then for member CD, we have the forces computed, CX7, CY7, CX45, BX45, and dy is yet to be computed. But obviously, there's only two forces along the vertical. So we have summation force along y equals 0, dy minus cy equals 0, and dy is equal to 7. Just equal to cy, which is, but the direction is upward, while cy is downward. Okay, so we could now draw shear moment diagrams for member CD. With the shear diagram, we start with 0, and we have a reaction here of 45 millimeters to the right. So we go to the right, minus 45, and then this applied load is giving us a shear which is positive because it's directed towards the left. So this value plus 15 times 6, minus 45 plus 15 times 6 gives us a varying shear from this value to positive 55 kilonewtons. And then we have a reaction CX45, so it goes back to 0 at point C. And this is our shear diagram. For the moment diagram, there is no moment there, it's 0. And at the center, we have to determine the moment there by this area. This is a negative area, so 0 to a negative moment somewhere. And this is negatively decreasing. Now the shear area is negatively decreasing, so the slope in the moment diagram should be negatively decreasing, meaning from maximum slope to 0. as I mentioned earlier, for columns actually, to draw correctly the moving diagram, we just imagine that we are looking from this direction, no, towards the member, and we need to rotate it 90 degrees and picture it out as a beam. Okay, so this column becomes a beam when we rotate it 90 degrees, and then we proceed with drawing the moving diagram. So the maximum slope actually is from maximum slope to zero at the center. The vertical line is zero slope actually, because again we rotate the column 90 degrees clockwise. So starting from zero here, it's maximum slope, and then goes to zero slope. And this is our moment diagram, the slope, the moment diagram. It's just like a beam subjected with a uniform loading, twisted 90 degrees. The moment is one half of 45 degrees, 45 kilonewtons times 3 meters, one half of 6. And then we have minus 155 kilonewton meters. And that value will just be added by this area, negative 135. As this area is just equal this area, positive 135. And the moment from here goes back to zero. This is positively increasing. Positive increases. Slope is zero, then gradually increases. And the final moment diagram is parabolic, meaning this is second degree because this first degree. The slope of the shear diagram is first degree, and this becomes second degree, meaning either parabolic or circular. And this is the moment diagram. It is a must that we have to combine all the moment diagrams, although we can also combine the shear diagram for the whole frame. But what is important is the moment diagram, so that the designer can see the behavior for the whole frame. So combining all the moment diagrams, we'll just present the frame by lines, so we can see clearly the behavior of the moment diagrams for the whole frame, not overcrowding the drawing or the figure. It's A, B, C, D, and for member AB, we have this moment diagram, start with 0, and then we have 180 kilonewton meters here. And actually this is negative for this column. For member BC, we have also this moment diagram. This the moment diagram we have, and we have 180 here. It's also negative. It's just equal to 180. At this point, we have 55.5, and then we have 10.5 millimeters. Goes back to zero. For column CD, we have this moment diagram, maximum of 135 kilograms. So this is what we can see, no? The actual the whole frame subjected with corresponding moments as they develop from the applied loadings. And from this moment diagram, we have to draw the elastic curve or the deformed structure. In frames, we call it deformed structure. That is the behavior of the frame in response of the movement, or because of the applied loadings that develop this movement. Each of the member will have to deflect and follow a deformed structure for the whole frame. So we refer our deformed structure from this moment diagram. Okay, this moment will cause bending towards the right, no, opposite. The moment that is developed on certain member will cause bending opposite where the bending moment is located. If it is this moment, then the bending is like this towards the left, and it will be zero slope at this point because we could not allow rotation in a joint which is fixed. So since B is fixed, The slope of the line in the elastic form or in the form structure is 0 here. But it's not 0 at this point. Now we can allow this point to rotate because this is pen connected. It can freely rotate. So this is the moment diagram for member AB, and then for member BC, we have here this moment causes bending upward actually. So it starts with 0 slope and then it bends upward. This is bending upward from this point up to this point where the moment is negative for the beam, and for this positive moment, it now bends downward. And then the location where moment is 0 is the transition actually, no? It's the transition from bending upward to bending downward, moment boundary, and we call that the point of inflection. Okay, so transition from bending upward to bending downward is the point of inflection. It gives us the location where we can freely make our splices for reinforcement, or even for steel beams. We can also splice it somewhere at the point of inflection because it simply means that that point is not subjected with any stress because the moment is 0, so therefore the stress is also 0. So we can make the splices, or in pouring of concrete beams, we can make the schedule of pouring that if possible it could be stopped if there are any eventualities of stopping of pouring due to heavy rains, or maybe some events that might not pursue the continuous pouring of concrete. We can stop the pouring at the points of inflection, at the point of inflection in this case, for the beam. So that's the important consideration that we have to take for the location, actual location, the point of inflection, so that we can have an idea as to where to splice or where to stop pouring the concrete. Splice reinforcements for beam column, beam reinforcements, or maybe splices for steel or any nickels for the beam. So, and then for the column CD, this one will bend the column to the right, to the left. This to the right, and that is there is no point of inflection for this column. It's also with the other column because there is no point where the moment crosses the 0 line. It's only in the beam where we can locate the point of inflection. So this is now what we call as the form structure. The structure uh, being subjected with the pile loadings and having developed the deformation because of the moments also which are developed. And we can see how the behavior is giving us an idea as to where to reinforce more, or what should be the magnitude of movement that we have used in determining the size, the dimensions of the columns, as well as the beam. And from the values that we have obtained, the column should be designed with this moment, 180 kilonewton meters, the maximum moment. The beam should also be designed using this maximum column of 180 kilonewton meters. They are meeting at a point where it is fixed, so therefore the moment is just, it should be the same, the maximum moment should be the same. So for the beam and the column AB, it has to be designed using this one. For column BC, CD, it has a maximum of 135 kilonewton meters, but it's not necessarily the value that we use in designing this one, because if we have to reverse the action of the uniform loading, it might be that this will give us a maximum moment also. We'll just understand that later in design. But at this point, we are just giving this moment diagram, the location of point of friction, and all the other data, maximum shear, to the designer. So the designer will just look at the critical values and make his design. So that's all for this example of frames.